So good afternoon, everybody. So last time I explained the timer system. As you see here in this picture, just give me 1 second. Yeah. So as you see here in this picture, guys, as I told you last time, we have 80 channels, right? Every channel has one pin on port T, right? And also every channel can act or can do one of two functionalities. It can do input capture or output compare. Okay, you can select one of them, right? Also, every channel can trigger interrupts. That's why we have 8 interrupts here, right? On top of that, we have a counter. This counter, as I explained last time, should count from 000 to 1111. Okay, and you can control the speed of this counting, right? Because this counter actually needs a square wave like this one, right? And for every cycle, it's gonna the timer is gonna be incremented by one. Okay, so uh, by controlling the speed of this frequency, you can actually control the speed of counting. And as I told you, this frequency actually is 24 megahertz divided by prescale. And this prescale can be a number from 1 until 128. Okay, just give me 1 second. Okay, so and you can program it, right? So yeah, and also I told you there is something we call a timer overflow interrupt. Until now I didn't explain why you need it. Today I will do, right? So here in the timer overflow, as you see here, guys, once the timer count from 000 to 11111, okay, and then after 1111 the next count is 000, and at this time we say overflow happened, and at this time trigger interrupt. So every time the timer rules from 111 to 00, actually it's going to trigger interrupt. We call it timer overflow interrupt. Okay. So that's what I explain. Also, I explain what is input capture. What is input capture? Okay, and how can we use it? The short answer is input capture is used if you want to measure time. Right, like for example, if you have a signal, something like that, guys, and you want to measure the time from here to here, right? Or you have two signals, you want to measure the time from here to here, and so on, right? Or sometimes I want to just measure the time from here to here, okay? From here to here. So if you want to measure time, input capture is used for that, okay? Very efficiently, because most of the work done by the timer, right? So microprocessor is not gonna or it's not gonna take too much time from the microprocessor, okay? How input capture works? Very simple, because the channel has a pin. When this pin has, like, you can program it. For example, I want to capture rising. Okay, so once the rising comes, once rising or falling, whatever. So once it comes, what's going to happen? The value, the current value of the timer, which is stored in a register, we call it TCNT, is going to be stored in a register, we call it TC, right? So we have 8 of TC registers. All of them are 16 bits, right? So we have TC0 for channel 0, TC1 for channel 1, and so on, okay? So this is actually, it's like this is the time for the event, or this is the time for the falling edge, right? So, and today I'm going to explain, or the main idea is that once I know, once I know what was the count here and what was the count here, I can know, and then I have to, I can calculate how many times the timer counted from here to here, and this is the time, right? this how this is how we measure the time. We need to know how many times the counter counted from here to here, and then once you know the number of counts, it's easy. You can convert to time easily, because every count should take 1 over f, and you already know what is f, right? This is how it is. Also, so once the event comes, rising, falling, whatever, once the event comes, so actually two things are going to happen. Number one, you are going to hear trigger interrupts, right? Also, this value is going to be stored in TC3. That's why I told you input capture also can use like IRQ, right? Because you can see the overlap between input capture and IRQ. IRQ, once every time you have event, you trigger interrupts. That's okay, right? But you don't store these values. This is the only difference, right? So here, yes, I can use input capture like IRQ, and I explained last time one program, and how to do it. I'm gonna come to this point. For output compare, okay, I told you for output compare, guys, it is used if you want to generate a square wave signal like this one, right? And you are gonna do it very efficiently. So how it works? It works this way. Look here, guys. I'm gonna put some value in the future. For example, if this is the value of the counter, I'm gonna add a number of counts, okay? So and put it here in TC3, right? So from here, the timer is gonna count. Once it comes to the value, I put it here. So this has to be a value in the future, right? After that, two things are gonna happen. Number one, output compare is gonna trigger interrupt. Number two, action has to be taken on the pin. So after this time, you want the pin to be 0 or 1, or you want to toggle it, right? This is something you can program, as I explained last time, okay? So that means I'm gonna have one interrupt here, and then I'm gonna say, please, next interrupt after 900 counts, right? This is in the interrupt subroutine. How you do that? This way. I'm gonna say TC0 should equal TC in T, which is the current count plus 900. So please toggle after 900 counts, right? How you came up with this 900 counts? Very easy. All what I did, I have here, I have the time. I'm gonna divide this time by the time of one count, 1 over f, and then I'm gonna get how many counts. Same thing here. I can get how many counts here, right? So what's gonna happen? Once I come here, so I should have one interrupt here. In this interrupt, I have to say TC0 equal TC plus 900. That means next toggle should be after 900, okay? And then after 900, as I said here, two things are going to happen. Number one, toggle. Number two, interrupt, right? So I'm going to have another interrupt here. In this interrupt, this time I'm going to say TC0 should equal TC plus 2100, right? So next toggle after 2100, right? So if you can see what I'm going to explain it today in some details, how this program, okay? And also, if you also can see a big overlap between output capture and RTI. Why? RTI is used if you want to make periodic interrupts. This one can do the same thing, right? Because here I put some value in the future. So I say after 900 make interrupt, right? So if I say here, if I come here, I say another 900 make interrupt, another 900 make interrupt, another 900 make interrupt, another 900 make interrupts, right? That's how I can make periodic interrupts every 900 counts or every 300 microsecond. And I told you, I like this one more than RTI. You know why? Because it's very easy to set the time, very easy. Because in this case here, 1 over f was like 1/3, 1 over 3. Let me get the thing here. So the time for one count, 1 over f, was actually 1/3 microsecond. Very interesting. That means I can control the time, the minimum unit. If I add 1 here as well, so 901, so actually I increase the time by 1/3 microsecond. Very interesting. And you can easily set the time, right? This was not the case in RTI. In RTI, we just had a table and you have to pick up from this table. Now, no, you have a full control on the time. You can easily change this time, the time of the interrupts, right? By increasing the number of counts. Very easy, right? And very interesting. This is one thing. Same thing, as I said, input capture can be used for as IRQ. And also, I like input capture even more than IRQ. Why? Because IRQ has limited options. You only have falling edge or low level, right? But input capture here, as I said last time, you can program it for rising, it can be for falling, it can be for both. So you can trigger interrupt every time there is rising and falling. Either one of them can trigger interrupts. Okay. So, and then I explained how can you program it. And for programming, I'm not going to repeat it because this is just similar to what we did before. No difference. Just all what you have to do. Number one, you have to do the same programming we did before for interrupts, right? But you have just used different numbers, right? As I explained. So nothing is new here. Also, you just have a bunch of registers and you have to manipulate, or you have to write some values to this register. So this is just very easy, right? I'm not gonna talk to. I make even a summary here. Also, how can you program input capture, output compare? It's almost the same thing, but you have to select the numbers from here. Also here, you just manipulate some registers, right? To select here, you can select if it is input capture or output compare, because every channel can be input capture or output compare. This is the enable bit, interrupt flag bit, and this is here. This is the action you want to take on the pin. Do you want to toggle, you want to clear, you want to set what action you want to take when the value you put in TC, right? When this value is equal to the TC in T, right? So when they are equal, what action you want to take in the future after 900 or after 2100 counts? What action you want to take on the pin? You want to clear the pin, you want to make it high, you want to make it toggle, whatever you can decide here. Also here you can decide what you want to capture, right? You can see here I use the 16 bits here simply because we have 80 channel. Every channel needs 2 bits, right? As you see here, 2 bits. Based on the value you put here, you can program the input capture for rising, falling, or both. Okay. Even I give you summary here. For C language, it's just very easy. Number one, you can use a bunch of function as we did before. So I already explained these ones. Or you can actually manipulate the registers this way. Okay. For here, yeah, also here for C language, I have to use a number in C language similar to what it did in RTI. So in RTI, I have to use number 6 so that the C language can know this is IRQ. For RTI, you have to use number 7, and same thing for all interrupts here, right? So you have to use the number here, the corresponding to each interrupt source. Okay, and then I give you also this program. How can you use input capture like IRQ? This, to me, this is very interesting. Why? Because now you can have up to 9 IRQs. You got what I'm saying? This is very useful because maybe you have here a fire alarm, maybe you have here a sensor, maybe you have a switch, maybe, so you got what I'm saying? Maybe in big application, right? So you can have up to 9 IRQs. Okay, and so for the final exam, guys, so all what I need to know, you to know for the final. Number one, how can we use input capture like IRQ? Actually, this program. However, this program, I think I do it for channel 0, right? So you need to know how to do it for all channels. Is that okay? So all what I need. So in the final exam, all what I need from you, how can we use input capture like IRQ? This program. That's it. But you need to learn it. So the way I explain it here, for only one channel, right? In the here I say channel 0. Maybe in the exam I need channel 3 and channel 7, for example. You got what I'm saying? It's easy. It's the same thing, just to change the numbers, right? So this is for this one. Also, last time also I explained how can we use output compare like RTI, right? And also this is, I need this one as well in the final exam. Okay, so all what I need from the final exam is only these 2 programs, right? RTI, how can you use output compare like RTI? Also, how can you use input capture like IRQ, right? But again, here I explain this example on channel 5. Maybe you should learn how to do it for all channels. Okay, so here maybe I explained quickly last time. Maybe I want to spend some time here. So here, as you see here, guys, I want to make interrupts every 1 millisecond. Okay, so look at the idea. Very interesting. I want to make interrupts every 1 millisecond, right? So I need to know how many counts I need, right? So all what I'm gonna do, 1 millisecond, this is the total time. I'm gonna divide it by 1/3 microsecond. Why is this one? Because this is the time for one count. This is the time for one count. How you got this one, right? This is actually 1/f, right? And as I explained before, f was 24 megahertz divided by prescale, right? So after I did the calculation, after I selected the prescale, I think the prescale is 8 here, right? So once I put the prescale of 8, so now this one 24 divided by 8 is actually 3. So if actually is 3 megahertz, right? So if 3 megahertz, now you can get 1/3 microsecond. So this is a time for one count, 1/3 microsecond. Very interesting. Look, microsecond is a very short time, very, very short time. We are talking about a third of microsecond. Very interesting. Okay. So that means in order to make 1 millisecond, the timer has to count 3,000 times. Okay, guys. So what I'm gonna do, very simple, very easy. All what I'm gonna do in one interrupt, I'm gonna say in one interrupt, every interrupt actually, I'm gonna say TC5 should equal TCNT, right? Plus 3,000. That means please interrupt me after 3,000. Is that okay? What about the pin? Because also this one has to manipulate the pin. I don't care about the pin. Okay, that's why one of the option here, I need to go back and show no action on the pin. I told you, if you look at the options, we have 4 options. Let me go back to show to you. Yeah, here, guys. Look here, guys. Yeah. So let me clear this one. So here, if you look at the action you want to take on the pin, you can set, you can clear, you can toggle, or actually you can select no action, right? So in this case, I don't want to take action, right? So here I'm gonna select no action. So I'm gonna put 0 0 so that no action is gonna happen on the pin. So actually, I'm gonna use output compare as RTI. Just I want to generate periodic interrupts, right? That's it. So all what I did here, guys, in this program, just here in this part, just to configuration. Nothing is new, similar to what I did before configuration. And then here I make a variable interrupt period, right? I put it 3000. So what I did here, guys, is inside the interrupt subroutine. So every interrupt subroutine, number one, I'm gonna clear the flag bit as always we do. Also here, as that's what I told you guys, TC5 should equal TCNT plus 3000. So every interrupt I'm gonna say next interrupt after 3000. That's how I can make interrupts. That's how I can make interrupts every 1 millisecond. Is that okay, guys? So again, if you see how easily I can control this time, right? Easily. So this is 3000 are gonna make 1 millisecond. What if I want to make it every 2 milliseconds? Just I'm gonna make this one 6000, right? Easily, right? And not only that, you can increase it even very little. Just the unit can be only one third microsecond, right? So you can increase it by 1/3 microsecond. Okay. So again, let me tell you the conclusion, guys. All what I need for the final exam, two things. This program, how can you use output compare as RTI, the program at page 57. But again, this is for channel 5. You have to know how to do it for all channels. Also, the other programs, how can you use IRQ, right? Input capture like IRQ, this one in the page 29. Also, you should learn how to do it for all channels. Okay. What I'm going to explain now, and probably also on probably on Thursday, maybe I'm going to take 15 minutes or 20 minutes in the beginning just to teach. But this not going to be in the final exam anyway. Okay. I will see. Okay. So now I want the next program I want to teach you guys is how can you measure time, right? So for example, if I want to measure the time from here to here, how I can do that? Okay. I told you that's easy. All what you have to do, for example, I have to see what is the count here. For example, here the count was 7, and now what's the count here? The count here, for example, was 107, right? So once I know what was the count here of the timer and what was the count here for the counter, all what I need to know so that I can subtract them in order to know how many times, for example, 107 minus 7, so the result 100. That means from here to here, the counter counted 100 times. Okay, so if you know the number of counts, you can multiply it by 1 over f in microsecond, right, in order to get the time from here to here. Very easy, right? However, it's not always that simple as I explained this way, right? So what I explain here is just a very simple case. In reality, it's not always like that. Why? I'm going to tell you why. If this is a counter, it's going to count from 0 0 0 until 1 1 1. Okay. What I'm explaining here, for example, I'm going to start from 7 and then I'm going to end at 107, right? So I'm going to only subtract them. This is a very easy case, not right? It's not always a case like that. What about if I start from here and then the signal was long enough, okay, so that I'm gonna come to here one time and then I go one another time or third time and then I'm gonna stop here at 107. You got what I'm saying? So that means you should not only subtract 107 from 7 from 107 and that's it. No, because it's already went several times. It went through it several times, right? So in this case, how we can calculate the time? Very easy. Here we need the overflow flag. The overflow of the timer overflow. I told you later. I'm going to explain how we need it, right? So because I need to know how many times you did overflow here, right? Because every overflow, it means you counted 2 to 16, right? From 0 until f. This is 2 to 16, right? So I need to count how many overflow happened, right? And then use it in the calculation. So now look here, guys, what I want to say. Now it's not enough to know this time and this time. It's not enough, right? So I need three things now. I need this one, okay, and I'm gonna call it H1. I need this one. I'm gonna call it H2. Also, I need to know how many overflow happened from here to here. Timer overflow, right? So I need to know the timer overflows from here to here, right? And then giving these these three data, H1, H2, and overflow, I can calculate the time. Okay, how? That's what I'm gonna explain here. Look here, guys. So again, the input capture should give you two values, H1 and H2, right? So in the first interrupt, because actually I need two interrupts, as you see here, guys. In the first interrupt here, okay, I'm gonna store TC0 in H1. H1 is a memory location, and the second interrupt here, I'm gonna store TC0 in H2, right? And then, so now I have two values. I need one more, right? And also look here. After the first interrupt, I'm gonna enable timer interrupts, right? Because I need to count. Listen to me. I need to count how many overflows from here to here, right? How many timer overflows from here to here, right? So I'm gonna start from here, right? That's why after, as you see right now, after the first interrupt, we're gonna enable the timer interrupts to start counting. And as you see here, in the timer overflow interrupt subroutine, I'm gonna increment. I need to know how many times it overflow happened here. Okay. Anyway, so again, I think we agree. We need three values in order to calculate the time. Okay. So how can you do that? There are actually, we're going to use one of two formulas. As you see here, you can use this one, right? Look here, guys. Period should equal overflow times 2 to 16, right? Because every one overflow means you count it from 0, 0, 0 until FFF, so it has to be 2 to 16 plus the difference, right? So this case should happen when H2 is greater than H1, which this case, look what happened here, guys. So for example, I started from here, okay, and then I came here, I trigger here one timer overflow, and then I'm gonna come to here, right? So if you do that, how much is the time? The time, number one, I already did a complete counting from 0, 0 until FF, which 2 to 16, plus the difference from here to here. Is that okay? You got what I'm saying? So you have to use this formula. However, if you look at the another case, if H2 is greater than H1, that means we started from here. Listen to me, guys. I started from here, right? And then I'm gonna come here, right? And then I'm gonna trigger interrupt here. And then when I come here, I'm gonna stop here, right? That means the first overflow should not be counted. You understand what I'm saying? The first overflow should not be counted as 2 to 16, right? Because you started from here. You didn't make a complete round. It's a different from here because I started from here and then I'm going to make a complete round here. Is that okay? So what I want to say, guys, there are two cases, okay? The first case when H2 is greater than H1. The other case when H2 less than H1, right? We can use the same formula for both of them. However, here, overflow should be -1, okay? So that's what I did. If you look here, guys, so here I'm going to use the period should be every overflow. Actually, you made a complete round, so it has to be 2 to 16. However, here I'm going to do it this way. So I'm going to subtract one from the. It should be one less, right? Okay. So this is how we do it. Okay, let me tell you, before I choose a program, let me tell you the summary, guys. The summary is, in order to calculate, the time from here to here, guys, I need three values. I need what was the count here. I'm going to call it H1, right? Also, I need to know what is the count here. I'm going to call it H2. And H1 and H2, who's going to give you H1 and H2? This is output compare interrupts. So output compare interrupts is going to give you these values, right? So you need to know this is in the first interrupt. I'm going to get this one. In the second interrupt, you are going to get this one, right? So I need to know if this interrupt number 1 or interrupt number 2, right? Also, after I get this interrupt, at this time, I need to know how many overflow, timer overflow happened from here to here. So at this point here, I have to enable timer interrupts, right? So here this is in the timer interrupts. So here I have to increment like number of overflows. Now, if you already have H1 and you have H2 and already you have the number of overflows, very easy, you can use this formula to calculate the period. Okay, guys, I'm going to choose a program now. Okay. So here I did this program twice. I did this program in assembly. Also, I did it in C. So I'm going to only teach the C. You know, assembly will be the same. Again, this part will not be in the final exam, but it's good to learn it, right? So here, as you see here, guys, the way I did it is, this is the main program. So if you look here, guys, I define this variable. They have to be global this way. So you have to put them global here. Why? This, you know, I know this is small mistakes. Students sometimes make spend too much time. This very small mistakes. You should not do it, right? So what I'm saying is that they have to be global because these variables are going to be used in the main program to calculate the formula, as I told you. Also, this one has to be in these values are going to be used in output compare interrupt subroutine. Also, it can be in the timer subroutine. Okay, so that's why it has to be global. So here I define these three variables. Okay, and then here I just do initialization here, nothing new, just initialization for output compare, right? And now look here, guys. I think I made a mistake. I'm sorry. Yeah, here I just initialize, I put 0. Sorry, it has to be here. I'm sorry. You got what I'm saying? What I said is correct, but they have to be here. I put it at the wrong place. Here I just put 0. So all these variables, guys, all these variables have to be global because they are going to be used in the main programs. Also, they are going to be used in the interrupt. So you have to program them here to be global. Okay. Now, look here in the main program. So after I did the initialization, guys, so input capture can work. So every time there is I think I program it here to react to rising edge, right? So this is the way I programmed it. So every time there is a rising edge, right? So it's going to be triggered, right? So here what I'm going to do, guys, I'm going to wait for 2 interrupts, right? Why you have to wait for 2 interrupts? Because I told you I'm going to get after I need to wait for 1 interrupt to get H1. Also, I have to wait for the second interrupt to get H2 and to get overflow, right? That's why I'm going to wait here. This is in the main program. I'm going to keep looping. I'm going to wait until we receive 2 interrupts, right? So these 2 interrupts here in the, this is output compare, guys, as you see here. This is the interrupt subroutine for output compare. We use number 8, as you see here. So every interrupt, I'm going to increment the interrupt by 1, right? So I have to wait until output compare is interrupted twice, right? Once it is interrupted twice, that means already H1, H2 overflow already got the correct values, right? So now just to do the calculation. That's what I did. So I did the calculation as I explained before. If H2 is greater than H1, I'm going to use this formula. Otherwise, I'm going to use this formula. Okay. The other. Okay. So now let's go to here. Very easy. Look here. Again, I used here number 8 because this is for output compare channel 0, output compare channel 0, guys. So let's see what I did here. What I did, guys, number here, for sure you have to clear the flag bit. We always do that. Nothing is new. Number 2, I have to increment interrupts number. Okay, I have to know if this is the first interrupt or second interrupt. Is this one or this one, right? If this is this one or this one, right? Because it's programmed to I did the I programmed it to trigger interrupts every every rising edges. Okay, so here if it is, that's why I increment here. If it is interrupt 1, that means I'm here, I have to do something. If it is interrupt 2, so that means I'm here, so I have to do something else. Let's see what you have to do. Okay, number 1, if it is in the, if this is the first interrupt, so I'm gonna store TC0 in each one, right? TC0. If you don't do that, TC0 is going to be overwritten. So next interrupt is going to override TC0. So I have to store it here, right? Number 2, I have to enable the timer interrupts because I need to start counting from here. I need to start counting timer interrupts from here. So originally, the timer interrupt should be disabled. And once I come here, I want to count overflows from here, right? So now timer interrupt is enabled. That means every time there is overflow, you are going to call the subroutine of the timer, right? We put here 16. And all what I'm going to do here, I just increment overflow by 1 because I need to know how many times the timer was overflowed, okay? Another thing which is very tricky, but you should learn it, very interesting to learn, that Also, you have to clear the flag bit. You know why? Honestly, when I did this program the first time, I forgot to add this one. Okay, but when I ran it, I found a mistake. It always the overflow is one more, one more what I'm expecting. So if I'm expecting 2 overflows, I got 3. If I'm expecting 3, I got 4. You got what I'm saying? So always there is one more. So I investigated and see why the overflows is not accurate. It's always one more. The reason was, okay, and this is something very interesting you should learn. The reason was because the timer here before this point, the timer interrupts was disabled, right? So timer are disabled, but that doesn't mean that this is the interrupt flag, right? So every time there was overflow before this point, before I enable, so the timer is gonna put 1 here, right? But there is no interrupt because interrupt is disabled. You got what I'm saying? So from the history before this point, okay, there was 1 here. That is why once I enable the interrupt, there was 1 overflow right away. You got what I'm saying? That's not what I want to do. I want to count how many overflows from here to here. But what happened once I enable the timer, there is already 1 overflow from the history. You understand what I'm saying? Because you can disable interrupts, but that doesn't mean when you disable interrupts, you are going to prevent the device from setting the interrupt flag bit, right? So what I did here, even one student even contacted me about this problem. I explained it to him. But anyway, so here I cleared, you have to clear the flag bit to cancel the history because I need to count overflows from here, right? This is if it is the first interrupt. In second interrupt, which should be here, I want to measure the time from here to here. So I'm done with this one. Here in the second interrupt here, again, this is 0. I'm going to put it in H2, right? And now I have to disable the timer interrupts. Also, I have to disable a channel 0 interrupts. Why I have to disable both of them, guys? Why? Because I don't want the program to mess up with the values I already collected. I collected 3 values, H1 and H2. If you keep output compare interrupts enabled, so for the next interrupt, you are gonna mess up with this value. So you're gonna destroy it. You got what I'm saying? So every time you want to do measurement, listen to me. So every time I want to do measurement, I have to enable output compare 0. I have to enable it, right? Once I enable it, and also I have to make sure the timer is disabled, right? So I have to make sure of these 2, right? And once it captures 2 values, so it's going to disable itself, right? So now I have the 3 values, H1, H2. Also, I have the overflow. You can just plug in this formula to get the period. Any question, guys? Okay. Let me tell you something interesting. So what I explained so far, guys, I explained how can you calculate the time from here to here. That is why I programmed output compare to capture only rising. Is that okay? Now, what if I wanna measure only from here to here, right? From here to here. What would I do? I wanna only measure from here to here, right? What would I do? Okay, I'm gonna tell you something also interesting, right? So someone can say, okay, that's easy. You can capture both rising and falling. So you can capture rising and falling. And this is going to solve the problem. So what's going to happen? I'm going to capture rising and then falling, and then I'm going to have the time here, right? Because this program is going to stop. It's going to stop after 2 interrupts, right? So if I can capture, okay, sorry, just give me 1 second. This is risk. This is not. So let me say. So what I'm saying here, I'm gonna program the output compare to capture both rising and falling. By this way, I'm gonna calculate this one, right? This is not always true. Very tricky. Very tricky. This is not always true. You know why? Because this depends on where you are gonna start the program. Okay. So if I start the program here, for example, so what's gonna happen? I'm gonna capture this one and this one, right? So here I'm gonna calculate this time, not this time. Right? If they are the same, it would be okay. If they are the same, but they may not be the same. The time may not be the same. You understand what I'm saying, guys? So if you capture both rising and falling, there is a risk, right? So if the signal is this way, if you start from here, that's okay. I'm going to capture these 2, right, and get this time. However, if you start somewhere here, you actually is going to capture this one, and then you are going to calculate this time, right? So what can we do now? So you are saying if you want to capture both, this may not be the best idea. I'm going to tell you what can you do. Very smart thing, very simple. Okay, look what I'm going to do. In the very beginning, I'm going to say I want to capture rising in the very beginning, right? So in the very beginning of similar to what I did, yes, this is what we did here. So what we did here, so I'm going to tell you, I'm going to do very little modification in this program so that it can capture both from here to here, right? So what's the little modification in the very beginning? As I did here, I'm going to say I want to capture rising, right? And then after I capture rising here, I'm gonna change the setting to capture falling. So I have to add instruction here. I have to add instruction here to change the setting so that we capture falling. I did that in the assembly. So let me go to, I think I explained it later. Yeah, look here, guys. So this program is similar to what I explained before. I just added one instruction here in assembly, right? You can do the same thing in C as well. So I added here one instruction so that you can capture the falling after you capture the first rising. Okay, guys? Just very little modification to this program. Any question, guys? Great. Okay. Now I'm going to move to output compare. Okay, for output compare here, I'm going to explain a program to generate a signal like this one, right? So as I told you, the first thing you have to do, guys, you need, as we see here, you need to you have to select a prescale. For example, I selected prescale of 8, and then after that you have to calculate the time of one count, which is 1/3 microsecond. Okay, and then I want to generate signal this way, as you see here, as you see this signal. Okay, so you have to convert the time into number of counts. So here this is 3000, right? So here I divided 3000 by the time of only one count. So this gives you 900. So here the timer should count 900 from here to here. From here to here, it has to count 2100, right? Because that's what I'm gonna do in the interrupt subroutine. In the interrupt subroutine, I'm gonna use this one. If I'm here, because as I explained before, guys, we're gonna have one interrupt here, and we're going to have one interrupt here, 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 and so on, right? So in this interrupt here, I'm going to say next time toggle after 900, right? And here I'm going to say next time toggle after 2100. Again, this one here, it has to be here. This one here. So every time I come here or here or here, I'm going to say next toggle after 900, right? And also every time I come here, so it has to be here or here or here, right? So I have to know. So now the question, how I can know if I'm already here or here, right? So how I can know that? Very easy. Similar to what we did in several places in this course, I'm going to use a variable. This variable, we already did it in several places. Like you remember in the LCD, if you want to know if it is on to make it off, or it is off, you want to make it on, same thing. So here I'm going to use a variable. This variable can tell me if I'm here or I am here. Because if I'm here, right, I have to add 900, but if I'm here, I have to add 2100, and this is what I'm going to do right now. So I'm going to choose a program, guys. Again, I did the program in both in C and assembly, so I'm also for just I'm going to explain the assembly here. Sorry, the C. So here in the C, guys, as I told you here, this is the high count, 900. This high count means when the signal is high, and this is the low count. I'm going to use this number when the signal is low, during the low, right? Also, I told you I need a variable in order to tell me if the signal is high or low, so that I should use this number or this number, right? So this variable is high or low, right? So this variable should always get values, guys, 0, 1, 0, 1, 0, 1, 0, 1. So here, for example, 0, 1, 0, 1, 0, 1. So every time I can know if the signal is high and or low, so that I can use this number or that number. Okay, so let's see the program. This is just initialization, so I'm not going to talk about this. Very simple initialization, right? So actually most of the program here, output compare is here. I decided to use channel 5, guys. That's why I used here number 13. 13 is for channel 5. Okay, the first thing I have to do here, very simple, very easy. You see right now, look here, guys. I have to clear the flag bit. We always do that. Okay. Number 2, I have to see if the signal is high or low, right? Using this variable, right? So if this variable is zero, right? So that means I here I'm gonna add the high count, right? Which is 900, right? So I'm going to add here 900 if it is 0. However, if it is 1, I'm going to add 2100 as you see here. And if it is 0, I'm going to make it 1. If it is 1, I'm going to make it 0, okay? So what's going to happen exactly, guys, is one interrupt, I'm going to be here. Next interrupt here. So one interrupt here, next one here. One interrupt here, next one here. One interrupt here, next one here. Because of the pattern, this pattern, the pattern of the high or low is actually 0, 1, 0, 1, 0, 1. So one interrupt here, one interrupt here, one interrupt here, one. That's why in one interrupt I'm gonna output 900, and in another interrupt I'm gonna output 2100, right? So and also I programmed, I'm gonna program for toggle. So every time there is interrupt, it's gonna toggle anyway, right? Very simple, very interesting. Okay. Any question so far, guys? Great. So now the good thing about this program, guys, you can generate, by changing this number, you can generate any signal easily, right? So I can make it like something like that. I can make it like something like that just by changing these numbers. You can even change the frequency easily just by changing this number, because this is for high, this is for low, right? You can just change these two numbers, the program will generate different signal, right? The next part I want to explain here, guys, I'm gonna explain. Let me see here. You know, I used in chapter 3, I explained how can you use the buzzer to make a police siren, right? Police siren, right? We did that in chapter 3. And the way we did it, guys, I put it in the main program. So this task was in the main program, okay? And as I told you before, many tasks, you can put it in the main program, or you can put it in one of the interrupt subroutine so that you can use the main program for something else, right? And that's exactly what I'm going to explain right now. So what I'm going to explain right now is similar to what I did in chapter 3, but the difference is in chapter 3, I did in the main program. Now I'm going to do it using output compare. So now I wanna use output compare to generate, because look here, guys, this pin is connected to BT5. BT5 is actually channel 5, right? So I can. So what I'm gonna do, guys, I want to generate a signal similar to the signal I've just explained right now. Yeah, where is it? Oh goodness. Yeah. Yeah, so similar to this program will generate a signal. Same thing, I want to generate a signal here to make a police siren. You remember in this program we generate a signal. I think, yeah, it was 500 hertz and 250 hertz signal, right? So in order to generate 500 or 25, all what I have to do, guys, is I have to convert, as I said. So for example, here, if it is 500, I remember this one was 1 millisecond and this one was 1 millisecond, right? So you have to know in 1 millisecond how many counts do you need, right? So in 1 millisecond, actually, if I divide 1 millisecond by 1 over 3 microsecond, as I explained before, so actually you need 3000. So if I want to generate this signal, guys, so here at this point, I'm gonna say next interrupt or next toggle after 3000. Same thing here also. It's gonna be also 3000, right? It's the same number, because this is the duty cycle is 50%. You got what I'm saying? That means this time is equal to this time, right? Don't be confused. Here, the duty cycle was different. That's why I used to do different numbers, 900 and 2100, right? So anyway, so if I want to generate 500 hertz, all what I'm gonna do, guys, I'm gonna modify the program I just made right now, so that I'm gonna use here 3000. Also, I'm gonna use here 3000, right? Now, if you want to generate 250, so actually 250, this one should be 2 millisecond and this one should be 2 millisecond, right? That means I need 6000. 6,000, this is the number I have to use here, 6,000 and 6,000, right? So now what I explain, guys, very simple, very simple. What I explain, very simple. If you wanna generate this signal, guys, your count has to be 3,000, right? This is the count you have to use. When I say TC5 equal TCNT plus this value, right? However, if you want to generate this signal, it's going to be the same thing, but instead of using 3,000, I have to use 6,000, okay? Now, so only one part is left. What is this? The part is, as we did in chapter 3, I have to generate this signal for half a second, and then I have to generate this signal for half a second, right? So how can we do that right now? It's the same thing as we did before. I need to count how many interrupts, for example, in order to generate this one. Because if you look here, guys, so here, this signal here, right? If you see in every cycle, okay, so I'm gonna have 2 interrupts in every cycle, right? 2 interrupts. So I have to see in half a second, in order to generate half a second, how many cycles you have, and you have to multiply it by 2. This is the number of interrupts. That means, listen to me, that means I'm gonna modify the subroutine right now so that I'm gonna generate this one for half a second. Half a second here means a number of interrupts. Then I'm gonna move to this one, right? And then after that I'm gonna generate this one, right, for half a second, right, also a number of interrupted, then before I move to this one, right? So I'm gonna show, this is assembly and the C. So I'm gonna explain the C. It's the same thing, but C may be easier to teach. So here again, if you look, how can we do this, guys? As you see here, I'm going to use this variable I used before, high or low, right? Because just I want to use the same. So here, high or low to tell me if I'm here or here. Actually, here it doesn't matter because all the time you're going to output 3000, but I want to use the same program I took before, right? On top of that, I'm going to make a new variable here, as you see here, guys. This new variable, it's going to tell me if I should generate high frequency or low frequency, right? So again, this is the same thing. This one is going to have a pattern 0 1 0 1. So this should be 0 for half a second, 1 for half a second, 0 for 1 second, and 1 for half a second. So this one should tell me if I have to generate right now high frequency or low frequency. Okay, as we'll see right now. So this is just initialization, just very easy initialization. This is the program is here. I'm going to tell you how the program works, guys. Look here. Number one, you have to clear the flag bit this way. Okay, you can kill it in a different way, but I explained how can you clear it using a function before. Now I'm clearing it using the manipulating the register this way. Okay, and now look here, guys, I should have a counter. Okay, because actually what's going to happen, I should have like high frequencies for some time, and then I should have like low frequency for some time. I told you half a second, right? So I need to count how many interrupts here before I switch from here to here. Also, I need to count how many interrupts here before I switch from here to here. That's why I have a counter here, right? So this counter actually is going to look here, guys. What I did, I'm going to say high or low. If high or low, if 0, right? If it is 0 and I already reached 500 counts, right? If you go to what I did in chapter 2, in chapter 3, it was actually 250. Because remember when we did 250 cycle, right? We did iteration 250 times, right? Because in every iteration we generate one cycle in every iteration, right? But here it has to be double. Why it has to be double? Because in every cycle we're gonna have 2 interrupts, so it has to be double, right? So because here I'm not, what we did in chapter 3, I counted cycles. Here I'm counting interrupts, and in every cycle we should have 2 interrupts, right? Same thing here. If you remember what we did in chapter 3, it was 125 cycles, right? So now I'm going to make it 250 interrupts, right? So anyway, so what I'm saying here, guys, if you see what I'm doing here I have, if the frequency I'm generating is 0, right, and then has 0, and I already have 500 counts. So now I have to move to the other frequency. How can you do that? The way I'm going to move to the other frequency, as you see here, guys, now I'm going to put 1 here. Also now I'm going to clear the counter because I need to count for from scratch again for the other frequency, right? Also I'm going to say now the high count or the high count and low count, what you have to use, it has to be 3000, right? So now I'm moving from the low frequency to the high frequency, right? Because this is the count here. Same thing here, guys. If this is already 1, right, and I reached 250, so now I have to move to the other frequency. How I can move to the other frequency? You have to clear the counter to count again, okay, and then you have also to make this one 0. Also, high count and 6000 should be this one. So again, guys, don't be confused. What I'm saying, this part, what this part has to do, guys, okay, this part has to update high count and low count every half a second, right? So half a second 3000, half a second 6000, right? This is what this part is about. And now all what I'm going to do after that, just similar to what I did before, I'm going to see if it is high or low. If it is high, so I'm going to output the high count. If it is low, I'm going to output the low count. So this is similar to what I did before. So nothing, this part is similar to what I did before when I generate a signal. This is just the new part here. This is only, this part is just the new part. And this is very easy. So here, so the counter has to count 500, right? To come here. Next time 250, right? Before it clear. And then we clear it, right? So this is how it is. You count 500 and then you clear. You start again 250 and then you clear. And then 500 again and so on, right? Is that clear, guys? Any question? Again, okay. It's interesting because as I told you before, and this is the most important thing, guys, in this course, actually. As I told you before, microprocessor can do a lot of things, right? Because of the interrupts, right? So you should learn. If I want to do too many things, you should learn that any task we did in chapter 3 and we put it in the main program, you can put it in any subroutine, right? So that you can make the main program free, and you can have several interrupt subroutines, so that every subroutine can do one task, right? So here, guys, what I want to tell you, every time output compare is enabled, very interesting. So every time the output compare is enabled, you run the police siren, right? What if I want to turn the police siren off? Very easy. Just disable the interrupts. That's very simple. It's like you have external unit. It's like you have external unit. If you want to run the police siren, just enable, right? Enable interrupt. If you want to disable, just disable interrupts. Okay, that's it, right? Because if you disable interrupts, it's not gonna come here. It's not gonna generate the signal, right? Any question, guys? Great. This is RTI as I explained. The last thing in this chapter, I'm going to explain the last thing here in this chapter, guys, this program. I'm going to tell you what is the main idea of this program. It's also very interesting program. Look here, guys. I told you when I generate a signal, okay, It's interesting. So let me, the good thing, guys, as I told you before, once no, it's not one. Yeah. As you see here, nothing is new in even in the timer system, right? Nothing is new. This is a good thing, right? It's, if you know how to do interrupts, how to manipulate registers, that's what we are using, right? So anyway, so now let me tell you something, guys. What if I want to generate a signal? The way you have to do it, guys, as I said, you have to count, you have to divide this time, right? You have to divide this time by the number of count, which is 1/3 microsecond, right? And then you have to toggle interrupt after that, okay? However, there is a limit. There is a limit. What is the limit? The limit is this count cannot be more, because it's TC and TCNT are words, right? So this count, the count you are calculating, it cannot be more than 535, right? Which for a word. So this is the maximum time I can generate here, right? So if you want to do the calculation, it's going to be 65,535. You divide it by 3. So I don't know how much is that. So you can 3. Oh, sorry. It's going to be divided 1/3 in microsecond. Anyway, you can calculate it. So what I'm saying, it's not too big anyways, okay? It's not too long. But anyway, so this is the maximum time you can for this part, and the maximum time for this part as well. You cannot do it more than that, okay? So let me tell you something interesting now. What if I need longer signal? Can I do that? What if I want to generate a signal, for example, 1 second and 1 second? Okay, and my maximum is here. I cannot do more than that. You got what I'm saying? So can I do it? Yes, you need to do like a trick to do it. It's not going to be direct, it's going to be indirect. Okay, so the way I'm going to do it right now, guys, here I'm going to say the action. look at the idea now, guys. Okay, so usually what we do, we say the action on the pin is toggle. That's what usually we do, right? And then I say, at this point, I say, please toggle after 900, right? Once I come here, I'm going to say, please toggle after 2100, and so on, right? So every time I read something, I toggle, right? So now I'm going to do it in a different way, because for sure, if you use the maximum time can be here. This is the maximum time, right? So I need to keep it high for 1 second, right? So the way I'm going to do it here in this interrupt, guys, I'm going to say, please interrupt after 65 535, right? And now I'm going to count. So this interrupt 1, this interrupt 2, right? And this is interrupt 3. Also, I'm going to say for the action on the pin, no action. So that's why I'm going to keep it high, no action, right? So I'm going to count. So this is number 3 until, for example, the one before the last one, for example, if this one is 17, for example, right? So the one before the last one here, I'm going to change the setting. I'm going to say, okay, now the action should be low. The action, so that next interrupt has to go low. You got what I'm saying, guys? Again, I told you we have a problem, right? The problem is, if you want to generate a signal, there is a limit on this time. Why there is a limit? Because the register is just 16-bit. I cannot put infinite number, right? So it has to be limited because it's just 16 bits, right? So here, so what if I want to generate like a big signal like this one? The way I'm going to do it, I'm not going to ask output compare to be toggle all the time. I'm not going to do that, right? I'm going to say here, no action. Here, no action. Then I'm going to count number of interrupts here. The interrupt 1, interrupt 2, interrupt 3. Once I come to interrupt 17, now I'm going to change the setting. I'm going to say, please, next time you have to make it low, right? This idea is very close to what we did in chapter 4, if you remember, when we tried to make 1 second. I told you guys, for example, the maximum here is 130 millisecond. That's why I told you I'm going to have one interrupt every 130 millisecond, but I'm not going to take any action, right? It's similar idea. So here, until interrupt number 8, remember, that's what I'm going to do in the coming lab anyway. So interrupt number 8, interrupt number 8, I'm going to, every 8 interrupts, which are equivalent to 1 second, I'm gonna trigger one interrupt, okay? So this is what I'm explaining in this program. How can you generate like big signals, like 1 second or something too bigger than our maximum? So I'm gonna tell you what I did here quickly. Here I'm gonna explain on the assembly because I didn't write the C for this one. So the idea here, yes, look here, guys. If I select the maximum time, which is this one, okay, so this is the maximum time I'm going to use, right? So if I select the maximum time, I found that this maximum time are going to make only 43 millisecond, right? So the maximum is 43 millisecond. That means if you want to make 1 second, so you need actually 23 interrupts, okay? In the example, I said 17, just as an example, but actually it should be 23, right? So what can happen exactly, this is 1 second, guys, okay? So every one piece here should be actually 43, and this is the maximum I can make, right? 43 millisecond, right? Until interrupt number 22, right? At interrupt number 23, now it is 1 second. And that's what I'm going to do right now. At interrupt number 22, I'm going to change the setting so that, so here is a set for all of these guys. I'm just counting, okay? And I have to select the action on the pin is no action. So I'm not going to change the status of the pin. If it is low, it's going to continue low. High is going to continue high, right? But here at this point, because now next time I have to make it low, I'm going to select it low or toggle, whatever you want to do, okay? So I'm going to explain, this is the main idea. So I'm going to tell you how it works. So here, I'm going to select this time. So this is the highest time I can select. This is just this part here, as you see. This is just for interrupt subroutine, right? Also here, this is just initialization. Now I'm going to talk about what you have to write here. Look here, guys. In every here, I have to clear the flag bit, as you see here. In every interrupt, I have to increment the interrupt count, right? As I told you, because until interrupt I told you until interrupt number 22, I'm not going to do anything, right? So I have to see. So every time I'm going to increment, and then I'm going to check if this is 22 or not, right? So at 22, I'm going to change the setting for next time. And that's what I'm going to show right now. So if it is 22, right, I'm going to say now you have to pull the pin high or you have to pull it low. It depends if the signal is already high or low. So here, 22 here. So next time I have to pull it low, right? If 22 is here, so next time I have to pull it high. You got what I'm saying? Because I'm going to count 20. I'm going to count 20. There should be 23 interrupts here and 23 interrupts here. Anyway, so this is the main idea. So I have to check high or low to see if this is high or low. And then based on that, I'm going to change the setting so that I'm going to change the action on the pin to make it high or low for next time. So when I set it here in this interrupt, I'm saying next time you have, this is the action I need for next time. Is that okay? And that's it. And now, all the time, the action of the pin, actually, I'm going to use 0, 0 because no action. So here, no action, no action anyway. Okay, guys? The other thing I want to explain, guys, is how can we measure the motor speed? So if you have motor, so this is the technique we use to measure the motor speed. So this motor, this is the shaft. Okay, on the shaft here we put a disc, as you see here, disc, something like as you see this disc, guys, and this disc has some holes, maybe 2 holes, maybe 3, whatever, and then this disc has to spin between these 2 devices. So actually it works this way. Look here, guys. We have infrared transmitter and we have a receiver this way, and the disc actually is running here. The disc is spinning here, right? So actually it looks like something. I'm not sure if you saw something like that before. Yeah, this is actually equivalent to this one. So one of them here, one of them is transmitter, the other one is receiver, and the disc here has to spin here, right? So actually what happens is that, look here, guys, when the disc, in this part of the disc here, right, there is no light. Okay, this part is going to block the light. That's why this transistor is going to be off. This is a photo transistor is going to be off, and then the output is 0. That's why you see the output here is 0. Okay, once one hole comes here, the light here is gonna strike the base of the transistor and then turn it on. So the voltage here is going to be 5 volt. So this is the pulses here. This one is equivalent to this hole, and this one is equivalent to this hole. So actually, that's exactly what happens here. Every time it's dark here, as you see here, once the hole come here, actually it's going to be generate one signal and so on. Okay, that means in every revolution, right? Every complete round, you are going to have 2 pulses, right? So you are going to have 2 pulses. So every 2 pulses, that means we completed complete round, right? So the idea here is that now I want to measure the motor speed. Okay, what it means, you want to measure the motor speed. I want to know how many revolutions per second, right? So the way I have to do it, I have to count how many pulses. I need to know how many pulses in 1 second, right? And then I'm going to divide this number by 2. Because every rotation or every revolution is equivalent to 2 pulses, right? So I need to count how many and then divide it by 2, right? And I already explained it before, very easy. How can you count how many pulses you have? So if I take this one to IRQ, for example, and IRQ, every time IRQ is interrupted, I'm going to increment it by 1, right? And then I'm going to enable IRQ for 1 second. So IRQ is going to be enabled for 1 second, right? And then after 1 second, I'm going to see what is the count. So this is exactly how it works. So in the main program, you can clear count in the main program, right? And then after that, you enable IRQ, right? Interrupts. Okay, and then you can wait 1 second. After that, you disable IRQ interrupts, right? After that, the count and in the IRQ interrupts, every interrupt, I'm going to increment the count by 1, right? And then after that, I'm going to divide this count by 2. This can give you how many revolutions per second. Is that clear, guys? Any question? Okay. Maybe this also, I just want to give you another application, another idea, how what I explained can be useful in some application. So for example, you can control using output compare input capture, you can actually control a machine like this one. So you have here container, and we have here conveyor, right? Conveyor. So conveyor, when the container come here under the valves here or under the pipes here, okay, so there may be some sensor. This sensor should generate a signal to input to IRQ, for example. So every time signal is generated, that means there are containers are there, okay, and the container needs to fill them up, right? And then what can we do? You can use IRQ or input capture, right? Because so here the way, so here the way I did it, I used input capture, but actually I used input capture like IRQ, right? Yes, right. I'm sorry for that, it's a phone. So anyway, what I'm saying, so every time there is a pulse this way, this pulse is coming from the sensor, right? So this one is going to go to input capture, right? So after that, so every time there is a pulse like this one, that means there are some containers here are waiting to fill them up, right? And then we have here valves. We have valves here, right? These valves are connected to actually output compare, right? So output compare is going to generate a signal for a certain time, for example, 1 second, 2 seconds, right? To fill this container up. Just one idea, you got what I'm saying? So that means that's what I did here, as you see here, guys. So here I'm just want to show you how can you use just an idea application. How can you use input capture, output compare? I can couple them together. So every time there is a pulse coming here, right? I have to open. I have here this output compare, guys, is connected to the valves, right? We have here like valves. Yeah, we have here something like valves to turn them on and off, right? So I can apply this signal. On them, right? So that I can turn them on for some time, and I have to make sure, yeah, this time is enough to fill up the container, something like that. So every time this comes, right? So we have to generate a signal like this one, and then after we generate the signal, this signal has to disable itself, right? So the interrupts, otherwise if you don't do that, we're gonna have like continuous interrupts. So output compare, after the second interrupt, right, or after you generate the signal in output compare, you have to write an instruction here to disable output compare 3, right? So that every time I enable output compare, is going to generate only one signal, and that's it, right? If you forget to disable it, so we're going to have like a periodic signals. No, that's not what I want to do. What I want to do, right? I want to couple input capture, output compare. So every time this one comes, this one generated, right? If this one doesn't come, this one is not generated, right? So it has to be this way. So input capture can be enabled all the time, right? This one is enabled all the time. However, this one, input capture is going to enable it, right? So when this signal comes, input capture is going to enable this one, and output compare has to generate a signal, and then after the signal has to disable itself, right? Waiting for another command or another trigger from input capture 1, okay, or another command from input. That's what I'm trying to explain here. So here, for example, as you see in output compare 3, I told you here you have to disable output compare 3 after in next interrupt, right? That's it. Okay? I already explained this one last time, right? So very interesting application. I explained it. Okay. Any question, guys, so far? Great. Also, I'm going to explain again all what I explained so far, only I told you all what I need. How can you use input capture like IRQ? How can you use output compare like RTI? But you have to learn it for all. Here in these slides, I give you example for one channel, but you should know how to do it for other channels. That's all what I need from this chapter, okay? Also, you need to learn it, guys, because I'm doing my best. We lost one week this semester because of the bad weather, but that's okay. I think the good thing is nothing new to learn. Not actually, or let me say it in a different way. What we did before, you can use it to like, for example, I now explain the timer system. Nothing is new. All what I are doing just interrupt us, right, and manipulate registers. That's it, right? So anyway, same thing for pulse width modulation. So I'm going to explain to you pulse width modulation. And if I don't finish it today, maybe I'm going to take just a few minutes on Thursday to finish it. But again, this one is not going to be in the exam. But again, you have to learn it because you may need it in your capstone. Okay. So what is pulse width modulation? Okay, guys, I told you guys our microcontroller, right? Has a lot of circuits, right? One circuit I told you about, the timer system, right? It has a hardware circuit for the timer system. I already explained the timer system. This one, don't be confused. This one has nothing to do with the timer system. I'm done with the timer system, right? This is something else, right? So here also it has one circuit for pulse width modulation, also has some circuit for analog to digital, also has some circuits for serial communication, and so on. You got it? So it has a lot of circuits here. Okay. Again, the way you can program it very easy. Once you know interrupters and how can you manipulate register, it's very easy. So now I'm going to explain pulse width modulation. Again, it's just a circuit of microcontroller. I'm going to tell you first how it is useful, how can you program it. Okay. So I'm going to tell you how it is useful, but let me explain the main idea here because it's really very interesting. Look here. Look here, guys. I told you before, how can we generate a square wave? How can we generate a square wave? Square wave, right? In digital system, we need to generate square waves a lot of most of the time. So it's very important to know how to do it. Okay. The way we did in chapter 3, guys. Chapter 3, I explained one way to do it. This one, pull, pin, high, right? And then I wait 1 second. Remember what we did? And then pull, pin, low, and then wait 1 second, and then repeat. Go back and repeat again, right? That's what we did in chapter 3. And then when we came to chapter 5 now, I told you, no, this was not a good idea. This was a bad idea. Why this was a bad idea? Because microprocessor is busy all the time, right? Busy all the time. That means I can say we are going to take 100% of the microprocessor time, right? 100% just to do this square wave. So that's why I told you that's not a good idea. When we came to chapter 3, I explained output compare, right? I told you here output compare also can be used to generate a signal, but this idea is much better than this one, right? So all what I need from a microcontroller, just subroutine here, execute the subroutine here, execute the subroutine here, and so on. So here, every transition here, we're going to execute the subroutine. That's it, right? So if you look at how much time this one needs from the microprocessor, for sure, this is much better than channel 3, much better than this one, because I'm gonna take very little time from the microprocessor. Okay, now we're gonna do a miracle now. Okay, but this one, yes, this idea is still better than the first idea. Okay, because we take here little time from microcontroller, right? Or microprocessor, right? Here in this idea. The second idea, I can use pulse width modulation. And the magic here, or the very interesting thing here, we're going to take a 0 time from microprocessor. So once you set the circuit is going to generate the square root forever by its own. Okay, very interesting. So here, number one, we have a circuit, right? All what you have to do, all what I need from the microprocessor, just to set the circuit. Just some registers, you have to initialize these registers. Right? Is that okay? Once you initialize the register, that's it. I don't need any time from the microprocessor. After that, it's going to be 0 from time from the microprocessor, because this circuit is going to take care of everything by its own. So it's going to generate a square root forever. So even there are no interrupts. I know students usually, because I have been teaching interrupts for some time. This topic, pulse width modulation, has no interrupts here, right? No interrupts. Very interesting. So it's like you have external circuit. All the microprocessor has to do, just to set the parameter, just to set the registers, initialize the circuit. Once you initialize the circuit, you need 0 time from the microprocessor. Very interesting, right? So that microprocessor can do other things. Okay, unless you want to change the frequency. So now I need time from the microprocessor. Unless you want to turn it off, you want to turn the signal off. But to drive or to generate the signal itself, I don't need any time. Like here, at least to generate the circuit, I need one interrupt here, one interrupt here, one interrupt here, one interrupt here, right? But here, no, you don't need any time, unless you want to do changes, right? Okay, guys. It looks great. So now we understood from you that pulse width modulation is something can help us, right? Very simple. So micro pulse width modulation can help us to generate a square wave very efficiently. Actually, it's not only very efficient with zero time from the microprocessor. Very interesting, right? Is that everything? No, this is not all the benefits. There is a big benefit now I want to talk about, right? The other benefit, the other major benefit here, it is very easy to change the frequency of the signal also, or it change duty cycle. Wow. Is it the second benefit? Yes. So now pulse width modulation has two benefits, or has two main advantages. The first advantage, you don't need any time. It doesn't have interrupts. I don't need any time from the microcontroller. Okay. Once you see the circuit, you are going to run this square wave forever. Very interesting, right? Again, as I said multiple times, the less time you take from the microprocessor, that means I can make bigger applications, right? This is the main thing, right? So anyway, so the second thing, you can change the frequency easily, very easy. You can also change the duty cycle. You know what is the duty cycle, right? So something like that, this is, for example, duty cycle can be 10%. The ratio of the high, as I explained it before, this is a duty cycle, something like that can be 90%, very high duty cycle. Anyway, so someone can ask me, okay, but why I need to change the duty cycle? The answer is yes. In some application, you need to change the duty cycle. Okay, in some application, for example, here I'm explaining only one application here, guys. So actually, as you see here, look here. If I go this way, actually I'm increasing the duty cycle, right? As you increase the duty cycle, you actually increase the average voltage, right? Makes sense, because this is 5 volt is going to take more time than the 0 volt. So actually you increase the average voltage. That means when I apply this signal, on some loads, like a fan, or like a bulb like this one, you can actually increase the voltage. When you increase the voltage here, so actually the fan can, as you go this way, the fan can rotate faster, right? So because you increase the voltage, for the bulb here, as you go this way, you actually increase the lighting, so it's going to be more lighting. So there are some loads. You can actually, sometimes we use this signal on this load to control it, right? So if you want to control the lighting, I can control this light, the brightness or the light, I can control it using this signal. Same thing for the speed of the fan. Okay. More importantly, also, this is used in a stepper motor. I'm not sure if you used stepper motor before or not. In a stepper motor, you have to generate signals with a certain duty cycle, certain frequency. So this also can be used there. And so let me tell you the conclusion before I give you details. I told you guys, number one, the pulse width modulation is just a circuit inside the microcontroller. This number one. Number two, it is very useful if you want to generate like a square wave, right? Efficiently, because after the initialization, it doesn't take any time from the microprocessor. This is number two. Number three, it's easy to change the frequency. It's easy to change the duty cycle. Also, I told you, because I have been teaching interrupts for some time, this one has no interrupts. Don't be confused, okay? So this is what we have here, guys, the pulse width modulation system here. In this pulse width modulation, we have actually 80 channels, like the timer, right? But again, don't be confused. This is completely different. This has nothing to do with the timer. So we have 80 channels. These channels are connected to port P, right? So that means you can generate 8 if you want to use all of them. For pulse width modulation, you can generate up to 8 signals. Okay, someone should interrupt me now and ask me, you are saying this is port P, but we used to port P before for something completely different, right? We used to port P to enable 7 segment, and also we used it for RGB, right? That is because I didn't use the pulse width modulation system. That means what I want to say is that, guys, if for example, you have 8 here, okay? Maybe I don't need all of them. Maybe I'm going to use only 4. Okay, now what I can do with these 4, right? So I don't need them. I don't want to generate signal. I don't want to use them as pulse width modulation, right? So what can I do? I can use them like a general, a general port, like port A, port H, like, okay. So that's what we did actually in chapter. Same thing, by the way, for BT5. BT5, we used it before as a general port to generate square wave, and also BT5 experiment, it can be used as input capture or output compare. Okay. Anyway, so the conclusion is, guys, we have 80 channels, as you see here. Every channel has one pin on port P. This is where you can generate the square wave. So you have up to 8. No interrupts, right? No interrupts here. And then all the story is, just make it easy, right? All the story is, we have just a bunch of registers. Just you have to write some number to this register. That's it, right? So this is the whole story. Okay. So now how it works, I'm going to tell you how quickly it works. You have a clock, right? You have a clock. I'm going to tell you later where this clock is coming from, but you have a clock. And then this is the signal I want to generate, right? So if I want to generate this signal, I have to say how big is the time from here to here, okay? And this, how big is this time from here to here? It's actually number. It should be number of cycles here. For example, if I say, and this number, you have to write it in this register, pulse width modulation period, because this one can determine the period. So here I have to put a number, for example, 100. What it means, 100? It means the time from here to here, right? This is the signal I'm going to generate, right? Should be 100 cycle out of this one, 100. Is that okay? Also, we have another register, we call it pulse width modulation duty. This is for a duty cycle, right? Again, the number I'm going to put it here. For example, if I see 50, that means the time from here to here is going to be 50 cycles from the clock, right? So now you have to register. This register can just to control the frequency, control the period, the frequency, right? This one can control the duty cycle. That means if I make this one 100 and I put here 30, now I have 30% to do the cycle. If I made 70, I made 70% to do the cycle, right? That is why I'm saying it's easy to change the duty cycle and also easy to change the period, because if you want to change the duty cycle, you have to manipulate this register and also this register. Anyway, guys, it's we finished. So I'm gonna explain it. I shouldn't take more than 15 minutes during the lecture, during the lab. I'm gonna explain it. You will find it's very trivial because we don't have interrupt. It's just a bunch of registers. I'm gonna explain them, and you have to manipulate these registers. That's it. Okay, guys. Any questions? We're gonna do a lab, as I said. Lab, I think number 10, right? The IRQ and RTI interrupts. We're gonna do it on Monday, and also I'm gonna meet you. Okay. Any questions? Okay. Have a good evening. Bye.